Hi, my name's Sam Kincaid.
And my name's Austin Muck.
I'm Abigail Robertson.
And I'm Adam Young.
And for our project, we designed an automated humidifier feedback control system. Growing plants indoors requires a lot of work and attention. One solution to take some of the workload off from this time-consuming task would be to create a completely automated humidifier feedback system. Humidity levels are among the most important factors to monitor when growing specific plants. If the humidity level gets too low, it could risk damaging the plants by drying out their leaves. On the other hand, if the humidity level gets too high, the plants could be at risk of fungal pathogen spore germination like botrytis, according to the article from the University of Connecticut. An automated humidifier feedback system would be able to keep the greenhouse or sunroom at constant stable humidity, which prevent these issues from occurring while also eliminating the extra work required to monitor the room and manually adjust the room's conditions to stabilize the humidity. The main goal for the feedback design is to set a desired level of humidity. If the room's actual humidity is too low, then the humidifier will turn on until the actual humidity matches that of the desired humidity. If the humidity is too high, then the fans will turn on and act as a disturbance to clear the humidity until the room reaches the desired humidity. To help measure the accuracy of the feedback system, the metrics include a set percent humidity desired of 70%, the area of the closed room being 18.6 square meters, and the area the plants take up in the room, which is 12.4 square meters. These variables are set as reasonable constants in order to be able to calculate a closed-loop transfer function. The plant within the feedback system needs both an actuator and a system. The humidifier will be the actuator because it turns on based off the set humidity level. The greenhouse and the plants will be the system because they are the control area being affected by the actuator.
The lump model our team went with to solve this problem was a tank inside of a tank. The larger tank represents the greenhouse, where the pressure of the fluid inside the room is the humidity. The flow in and out of the tank represent the source humidifier putting humid air into the room, QH in, a fan pushing air in, QF in, and pulling air out, QF out. The fan's resistance values were chosen based on a greenhouse catalog, who posted a fan calculator which, based on our desired humidity, gave us our optimum ventilation CFM rating. The humidifier's resistance was determined based on the maximum output given by a basic humidifier given our greenhouse size. Looking at the smaller tank, this represents the plant or plants whose seen humidity we are trying to regulate, and the area is the plant's surface area. The pressure of the tank represents the humidity of the plants. The humidity coming in and out are represented by the flows QP in and QP out. The resistance value of the humidity coming into and out of the plant were determined by researching how much moisture a plant's leaves absorb during the day and how much a plant's leaves respire at night. The information was given by Robert Rister in an online forum.
Here you can see the transfer functions for both the humidifier and the fan respectively. Since these are both open-loop functions, if implemented, would grow to their final step response values with no self-adjustment. Given our open-loop block diagram, see that our desired humidity, modeled as the reference input, will be set to 70%. Our plant system will contain our humidifier and an ordinary gain setting of 1. The disturbance, which will be a constant, will remain unaffected from the plant itself. Our final value and expected plant output will be to achieve our reference input of 70% humidity. Here you can see a simulink model of our open-loop block diagram, which was shown in the previous slide. The scope block element was used to watch a live time delay response of our system during testing. The step block function will indicate the on-off activation of the humidifier.
According to the Bode plot analysis of our open-loop transfer functions, both the humidifier and the fan are stable. We can see this because a change in slope of the magnitude plot reflects the same change in slope of the phase plot. This means there are no poles or zeros in the right half plane. Due to the fact that a greenhouse does not need instantaneous changes in humidity, our plant is fast in application. There is an outside disturbance our system will encounter when the doors to the greenhouse are opened, allowing people in and out of the room. Our plant will constantly be adjusting based on the actual humidity of the room to output the desired humidity the user sets. The actual humidity of the greenhouse then acts as a reference input that our plant will need to follow.
We wanted our rise time less than half of a second and our settling time less than 2 seconds. We were willing to sacrifice some rise time in order to decrease our overshoot value specifications. We designed for our steady state error to be less than 1, and we will discuss how we verify this in the upcoming slides.
A PI controller has been chosen because it is commonly used in industry for temperature and liquid and gas volumetric flow scenarios, and secondly because of its simplicity. Here we will choose our plant model to make it a feedback response system. Now that it will be receiving input from our output value, we will introduce a PI controller to regulate system behavior.
Based on the Routh-Horowitz analysis of our transfer function, the system is Bible stable for a K value greater than negative 0.021764. Through steady state error analysis, we found that our step input value to be approximately 0.79 and our ramp input value to be infinity. This tells us that our system cannot handle a ramp input error but can handle a step input error. A higher DC gain would give us a step value error closer to 0, which would give us a higher accuracy in response to error.
Yep.
Our analysis of the transfer function reports a rise time of 0.00324 seconds and a settling time of 0.00567 seconds. This data verifies our design requirement of having a rise time of less than half a second and a settling time of less than 2 seconds. This shows that our system performs much better than we had originally expected. From our Bode plots of our system, we discovered an infinite gain margin and a phase margin of 116 degrees. This infinite gain margin tells us that our system is inherently stable. A higher phase margin also indicates stability. According to Lecture 30, gain and phase margins are measures of robustness of a system to uncertainty.
For our test of robustness, we chose time delay. First, you can see we plotted the step response of our feedback control system to see what we should compare the different time delays to. This shows that after 15 seconds, our step response levels out to an amplitude of 1. We used the transport delay function to simulate different time delays. After implementing different time delays from 1 second to 10 seconds, we were able to find that our system could handle a 2-second time delay and still settle out within the 15 seconds we saw undisturbed. This means that for our time delays less than 2 seconds, our system is robustly stable. In conclusion, we have presented a feedback control system for a greenhouse which will use a minimal amount of devices and keeping costs down. Furthermore, our system will still sharply respond to a change in its surroundings, leaving the operator with minimal responsibilities. Thank you for your time.